Due to its molten iron core, the Earth has a magnetic field around it, just like a bar magnet. This magnetic field extends outwards into space, forming a big bubble that we call the magnetosphere. The inner layer of the magnetosphere, from near the Earth's surface up to 1,000 or so kilometers, is called the ionosphere because it is made up of particles ionized via radiation from the Sun. In low-frequency radio astronomy, when we point our telescopes to the sky to measure the faint signals that travel through space to reach us, we need to take structures and perturbations in the ionosphere into account that might change these signals. We need a good understanding of the effects of the ionosphere to make sense of our data. Pictured near the surface, the Earth's magnetic field lines run parallel and come out at an angle to the ground. It has long been postulated that tubular plasma structures go along the magnetic field lines, and it is structures like these that can affect our astronomical measurements. Previously, people could only guess what they might look like, since no one has ever been able to image them. My name is Cleo Loy, and I am an astrophysics student with Castro at the University of Sydney. I have found that we can use a new type of radio telescope to not only detect these plasma tubes in the ionosphere, but to actually image them. And what's more, we can reconstruct their behavior in real time and in 3D. This is a very exciting world's first. The Murchison Wide Field Array, or MWA for short, is a radio telescope in the Western Australian desert. It consists of 128 receiver tiles, spread over a circular area roughly 3 kilometers across, that work together as one instrument. What makes it so special is its huge field of view, letting us observe a large patch of sky and all sorts of celestial objects as they flash or pass overhead. We use the MWA to study how the ionosphere shifts around the observed positions of objects in the sky and distorts them. A good analogy for this is the way lights at the bottom of a swimming pool dance around when the water ripples. We cannot see the water directly because it is transparent, but from the dancing lights we can determine the pattern of the ripples at its surface. Just like when we are looking at an angle down parallel train tracks, if you were standing at the site of the MWA, the Earth's magnetic field lines would appear to converge. What we saw with the MWA was a stunning distortion pattern that strongly coincided with the magnetic field lines. For the first time, we revealed the true nature of these structures as a vast array of plasma tubes, filling the sky in staggering numbers. The MWA's rapid snapshot capabilities allow us to make movies showing their motions over time. But that's not all. The MWA also has the power to see in 3D. When we look at an object, our brain combines the images from our two eyes, allowing us to judge how far away it is. So by analyzing the signals recorded by MWA tiles in the east, separate to tiles in the west, we give the MWA the ability to perceive depth. This has never been done with a radio telescope before. By using the MWA like a pair of eyes, the three-dimensional nature of the tubes springs into reality. We can measure their heights above the ground, see their steep inclination, and watch as they drift sideways towards or away from the MWA. This is a whole new way of looking at the sky.